Hello and welcome to another power system analysis class. In the previous class, we spoke about three phases, Y and delta connections, and how we convert Y connections to delta connections. We gave an example on starting a three-phase motor. Do you remember what type of connection do we start a three-phase motor, star or delta? Yes, or Y, star is Y, yeah. So we start with Y and then we switch to delta. Do you remember why we start with Y? Yes, lower starting current, lower torque. So you wouldn't gonna put less pressure on the motor and then we switch to delta connections. We spoke a little bit about per phase analysis. Today we will dive deep into per phase analysis and how we do per phase analysis. Per phase analysis are used for balanced three-phase analysis, and it's to simplify three-phase analysis. Instead of doing the analysis on all three phases, we pick one phase and we do our analysis on that one phase. So it's like treating a three-phase system like a single-phase system. So in a balanced three-phase system, all loads and source are Y connected, and we have no mutual inductance between phases. We would neglect that. Now, to do a per phase analysis, first of all neutrals are at the same potential. All phases are completely decoupled. All system values are the same sequence as source, and the sequence that we had was phase B lagging phase A and phase C lagging phase A. This is known as a positive sequence. We would also explain about negative sequence and zero sequence later on as well. Now, to do per phase analysis, we convert all delta load or sources to Y's, to equivalent Y's. We solve phase A. We pick one of the phases. We can pick phase A, B, or C, independent of the other phases. The total system power S is going to be 3 VAIA conjugate. And if instead of A, we pick phase B or C, they can also be determined, but the only difference is that we have a 120-degree positive, negative, depending if we pick B or C phase shift in the system. If necessary, we go back to original circuit to determine line values or internal delta values. Now, let's solve a per phase example. And this gives us a good picture on how we can solve and how we do a per phase analysis. So for this example, we assume we have a three-phase Y-connected generator with VAN of 1 volts with 0 degrees, which supplies a delta-connected load with Z delta is negative J ohms through a transmission line with the impedance of 0.1 J ohms per phase. The load is also connected to a delta-connected generator with VAB is 1 with a degree of 0 degree through a second transmission line, which also has an independent impedance of J.1 ohms per phase. We want to find the load voltage VAB or VA prime B prime, the total power supplied by each generator, SY and S delta. So this is the graph for this example. This is the circuit for this example. We have a three-phase Y-connected source, which you can see on the left. Let me bring my pen. So this is our generator. You can see here. And we have the load here. We have a second generator here. So again, I'm going to show the load with L, the generators with G. And in between, we have our transmission impedance of J.1. The first thing that we need to do is to convert all the delta, everything to a Y connection. So I need to connect G2 or the generation number 2 and the load to Y connection. Now, the question is this. If I want to convert the delta connection, the delta connected load, if I want to convert it from delta to Y, what is our equivalent load? So now load is negative J for each phase. If I convert this to a three-phase like this, what is my new impedance going to be? Are you sure? Perfect. As you remember from the previous class, Z delta, sorry, I don't know what happened. Just give me a second to see if the screen comes back. There's a problem with this cable. Okay. So we know that Z delta is, ZY, let's write it this way. ZY is equal to Z delta over 3 for each phase. What about the source that we have, the other generator? If I want to convert that to a Y source, what is the voltage of each phase going to be? So do you remember what was the voltage of the source? Voltage of line to voltage of phase relation in a delta connection. So in a delta connection, let me put it this way. In a delta connection, V phase, what is its relation to V line? What is the relation between V phase and V line? No. Let me show it again this way. This is our phase voltage. It's VAB. And it's also our line voltage. So V phase is equal to V line. But what about a Y connection? So if I want to connect this and replace this with a Y connection, if I want to connect this to Y, what is the voltage of a Y connection? The phase voltage compared to the line voltage. Do you want me to go back to the previous? I think it's better to go back to our previous. So just a reminder. So just to do a quick reminder, where was it? I think I had it here. So again, ZY, as mentioned, it's Z delta divided by 3. Okay. And what about the voltage? I can go back here. in a delta y connection, in a y connection, v phase is square root of 3 v of line. Do you remember this? So v line, square root of 3 v phase for y connection. I line is I phase. But for delta connection, I line is square root of 3 I phase, and v line is equal to v phase. Now, if I want to go from a delta connection to a y connection, then if the line connection here is, let's say, 1, in a y connection, it's going to be 1 divided by square root of 3 of that v line. Okay. And then I will separate each phase. So I'm going to have 3 phases. I'm just going to pick one of these 3 phases. So imagine this is replaced by a 3-phase y connection. And also this is replaced with the 3-phase y connection. And assuming that all neutrals have the same voltage and that are connected together, I would just pick one of the phases. So I'm going to pick these 3 phases here. These 3 single phases here. 1, 2, 3. And also we have the impedance between them. So if I convert that, it's going to look like this. I have 2 sources, 2 generators, and 1 load in the middle. The impedance for the delta was negative J. For Y is going to be negative J over 3. The voltage for delta was 1 with the degree of 0 degree. Now it's going to be 1 over square root of 3 with the degree of negative 30 degree, which as I mentioned, they have a 30-degree shift when you add them together. And the source on the left, you don't touch it. It's going to be exactly the same. And the impedances, again, you don't touch. It's going to be, again, the same. Now, to solve this, we will do a KCL for this point A prime. And by the way, we can rename it as A prime and A double prime. Now, if I want to write the equation for this, the KCL would be V of A prime minus V1 divided by its impedance. Yes? And then again, V of A prime minus this voltage, which is going to be V2, I'm going to call it V2, divided by its impedance, and V of A prime minus 0, because this is ground, divided by this impedance. So I have 3 currents. I have 1 current going this way, 1 here, and 1 going down. So I'm going to call this I1, I2 is going to be equal to I3. So I1 plus I2 is going to be equal to I3. Or I can write it like I1 plus I2 plus I3 gives us 0. One of them would be. So another way to write it, it's like this. I1 plus I2 plus I3 is going to be equal to 0, and I3 is negative because it's the opposite direction. Okay. So this is another way, better way to write it. Now, if I want to find I1, can you help me with I1 and tell me what I1 would look like if I do a KCL and Ohm's law? VA prime, this voltage, minus V1, which is 1 with a degree of 0 degree, over J 0.1 ohms. Am I correct? Now, 1 over J is equal to what? Do you remember from complex numbers? What is 1 over J equal to? It's going to be negative J. 1 over J is negative J. Yes? What is 1 over 0.1? 10. So 1 over 0.1 J is going to be negative J10. So this would be equal to VA prime minus 1 with the degree of 0, negative 10J or J10, which is this part. Now, what is I2 or I3? Same way, I2 would be VA prime minus 1 over the square root of 3. Again, 1 over 0.1J is going to give us J10. And for this one, 1 over negative J over 3 gives us 3 over negative J. In other words, it gives us 3J. Is it clear where we got these equations? Okay.
Is 30 degrees.
30 degrees. Okay, thank you. That's a great question. Let me bring that back up. So, do you remember when we converted that? VAB, or the voltage, is going to be this. Yes. Why? Because when you add these two phases, you're going to have a phase that comes up with a 30 degree. You remember when we added VCN and VAN, then we got VAC, for example, or VAB. If I add VAN and VAB, I get this. Actually, I get this current over here. And this is negative 30 degrees. I'm sorry, get this voltage, and this is, now this is VAB. Gonna have a 30 degree shift, okay? That's the reason when we converted this delta to a Y, it's going to be converted with a negative 30 degree. It's originally positive 30, but when 30 goes from the denominator to the numerator, it becomes what? A negative, yeah. Is it clear? Yeah, okay. Now, that's the reason, by the way, I posted the first homework. Did you see it on its complex numbers? You have, I think it told this weekend to turn them in. Please go and solve that. That's very important. Again, that's the reason I spend like almost a week on complex numbers, because from now on, everything is just done with complex numbers. It's a very important topic for all your courses in electrical engineering. Now, to solve the circuit, you write the KCL equation at A prime. And when we do that, we add these three, we convert the polar form to a rectangular form, and we can calculate it. And finally, what we get, it's going to be VA prime is going to be 0.9 with a degree of negative 10.9 volts. V prime C is going to be, again, the same amplitude, but by adding 120 degrees. V prime is going to be, again, the same amplitude with another 120 degree shift. And finally, the line to line voltage is going to be square root of line to phase voltage plus 150 degrees, which gives us 1.56 with a degree of 19.1. Or this plus 30 degrees. If you add this plus 30 degrees or this one plus 150 degrees, it doesn't make any difference. So it's going to be square root VAB is going to be square root of 3 VA prime with the degree of the alpha of that plus 30 degrees. So if VA prime is going to be equal to 0.9, VAB prime is going to be 1.56 with a degree of 19.1 degrees. Now, if we want to find each generator's power, for the Y generator, it's going to be 3 VAIA conjugate, which is going to be 3 VA, and the IA is going to be the difference between the voltage, VA and VA prime, which here is going to be these two voltages. So I can find this current, IA, divided by its impedance. So it's going to be VA minus VA prime over J.1 conjugate. And if I do that, I get 5.1 plus J 3.5 volt amps. And for the delta, I can again use the equation, but I need to find the voltage between these two because it's the delta, and then it's going to be 3 times that times the voltage, and gives us negative 5.1 minus J 4.7 volt amp. What does this negative mean, and what does this positive mean? Do you know? So this means is one of the generators is actually consuming power, not producing power. When you have two generators connected to each other, one is going to be the consumer. So that's the difference. So the direction shows which one is consuming power, which one is producing power. So development of line models. To develop a simple, let me do a quick quiz for attendance again. And I actually graded the previous quizzes as well. I forgot to bring it. I will give it to you on Monday. We want to do the same example, but this time, and you're going to have the same question in your first exam as well. Instead of J.1, we're going to have J.2. And this is J.2. And this is J2, J2, J2. This would be one with the degree of 30 degree and one with a degree of 30 degree. Or no, let's not make it very complicated on this. So J.2, J.2, and J2. And we want to find, the only thing that I want to find is V prime A. We just want to find V prime A or VA prime. Let me bring some papers. You can start working on it so I can bring.
So I think it would be great to check on the status where it is. There. And but then you have it, right?
Yeah.
Right?
Yeah. I have a paper. Please first draw the single phase, the per phase, and then solve it. Okay, did you all solve it? So the only difference that it's gonna, or do you need more time? Yes? Do you need more time? Okay, I'll give you a few more. Okay, did you solve it? Or need more time? Okay. So the only difference between this and the previous one is the impedance of the delta load and also the transmission. And if we have J.2, then this would be negative 20J, and this would be 3/2J. Did you have the same? Get the same? Yes. So again, this is going to be V prime A minus 1 with a degree of 0 over J.2 and J.2. Sorry, it's going to be negative J5. Negative 5J. Negative 5J here. It's going to be V prime A minus 1 to the degree of 0 degree times negative 5J. And this, when we convert a delta to Y, the impedance is going to be negative 2J over 3. So negative 2J over 3. If it's in the denominator, if it goes to the denominator, it becomes 3/2 times J. Is it correct? Did you get the same? Okay. And I'm not going to go through the process of solving it. What was the final answer that you got? What is V prime A? Tyler, what did you get? None of you? No? Okay. It should be less than 1. V prime A should be less than 1. I'll make this a homework and give you this as a homework. So this that you did right now, it's going to be attendance. And if you solve it partially, I'm going to give you the full grade, but I'll give you this as a grade, as a homework for this weekend. I will give this example for your homework this weekend. And you need to solve all V prime A, V prime B, and also the Y and delta power. Now, for the development of line models, the goals of this sections are to develop a simple model for transmission lines, gain an intuitive feel for how the geometry of a transmission line affects the model parameters. So the most common methods for transmission lines are the overhead AC, underground AC, overhead DC, and underground DC, and some other methods. We also have underwater cables as well. Depending on the distance, if distance is less than 500 miles, DC is not economically viable. Everything above 500 miles, because DC requires a rectifier first to convert AC to DC, and at the end you need a powerful inverter to convert that DC back to AC for residential or commercial use. So if it's less than 500 miles, it doesn't offset the cost to the amount of loss that you have. But if it's over 500 miles, it has some benefits, because DC, the first benefit of DC is DC, you don't have any, you would have significantly less inductance, and therefore you're going to have significantly less loss in the system. Other problem with the DC is when you get high voltage DC, you're going to have limitation on how you can regulate the power. Let me give you an example of a transformer. And this was actually an interesting question from FE. If we have a transformer, are you already familiar with transformers? Okay. And if this is connected to 2000 volts, let's make it 200 volt. Imagine if this is connected to 200 volts. N1 is 10. N2 is 1000. What is V out gonna be? $20,000? We think it's 20,000. So the options are this. 2, 2,000, 20,000, 0. Who thinks it's 2? So for a transformer, V1 to V2 is equal to N1 or to N2, which is equal to the N. 2? I'm sorry? Can you?
DC can work.
Perfect. This is actually 0. DC wouldn't work with transformers, okay? This was the exact question from FE. Transformers don't work on DC. So what you want to do is you need to convert that DC first to AC, run it through a transformer, and then go back. So this doesn't work at all. It creates just a huge magnet. You don't convert, you don't transmit the power. That's the reason DC failed at the beginning. In the war, they call it the current wars between General Electric and Westinghouse, which was Edison and Tesla. Edison went on DC, but the problem was you couldn't increase the voltage. You were stuck with the voltage that you produce in the generation side. But AC, you were able to manipulate you were able to increase the voltage and decrease the current to be able to transmit it for long distances. So for DC to be the voltage to be increased, you need power electronics, you need choppers, and those become very expensive and very high voltages and high currents. So if it's a short distance, like 10 to 30 miles, you're going to spend a lot of money on the power electronics, and it's not going to make sense. Is it clear? Okay. Now, before we continue with transformers and everything, and we're going to have a whole, chapter on those. This was just for you to just remind you of why we don't use DC. Again, we need a chopper at the end. We need a rectifier. We need inverters. It's going to be very, very expensive. Before we start with our next topic, which are transformers and motors and so on, we need to go through some magnetic laws and a quick review on magnetics. First, we have the Ampere's law. So it's going to be the integral of HDL, which is going to be A, IE, F, which is the MMF, the magnetomotive force, or magnetic force, what we call it, MMF, which is measured in amp turns. H is the magnetic field intensity, which is measured in amp turns per meter. dl is the vector differential path length, which is measured in meters. The integral is the line integral about closed path of L. And I'll show you what it is. dl is tangent to path, and IE is the algebraic sum of current linked by that. So imagine we have these two. One is a circle and another one is the line. Line integrals are a generalization of traditional integration. The first one is the integration along x-axis, and the second one is the integration along a general path, which may be closed. So definitely you're going to have different magnetic fields in this. If you use we use the right-hand law, the direction is your thumb. This gives you the magnetic field, if it's going inward or outward. But for the second one, what happens is you're going to have this part going out, this part also going out, this part going out, and so on. So you're going to have an intensified magnetic field at the middle of this circle, okay? That's the reason we put these coil in circles, because we want to intensify the magnetic field. This is how they build actually these magnetic, they build these speakers. If you want to build a magnetic catapult, you just, if you put a needle in between these and put 4 or 5 of these loops, you can accelerate that needle or that nail. And it's the same principle that we use in some electric, what we call maglev trains as well. And the first one we use for linear motors as well, and I'll explain more about that later on. The Ampere's law is most useful in cases of symmetry, such as with an infinitely long line. Now, another parameter is magnetic flux density. Magnetic fields are usually measured in terms of flux density, which would be, which is the flux density. It's measured in Tesla or Gauss, and 1 Tesla is equal to 10,000 Gauss. Now, you may heard of the power of an MRI device. They usually measured in Tesla. They are like 1.5 Tesla. fMRI device is like 10 Tesla. 1 Tesla is a huge number. It's a huge number. That's the reason we, in normal applications, if you want to measure the magnetic field around a magnet, motor, or an inductor, we use Gauss, because 1 Tesla could easily, if someone is in an MRI device with 10 Tesla, and they have an implant, a metal implant, it could easily rip off that. It's going to be very dangerous, very, very powerful. For a linear magnetic material, B is going to be mu H, where mu is called the permeability. The permeability for air, for example, is 4 pi times 10 to the power of negative 7. And mu is equal to mu 0 mu r. Permeability of the free space is 4 pi times 10 to the power of negative 7. Relative permeability is almost equal to 1 for air, as mentioned. So for air, it's going to be 4 pi times 10 to the power of negative 7 times 1, which is 4 pi times 10 to the power of 6. But if you have a metal, it's going to actually be a little bit higher. If you have, I don't know, a insulator, it's going to be a little bit. So depending on which material you're going to use, it's going to be different. Total flux passing through a surface A, phi is going to be equal to the integral of B dA. dA is the vector with direction normal to the surface. If flux density B is uniform and perpendicular to an area A, then phi would be equal to B A. I think you had most of these in physics magnetics already. Now, assume we have an infinitely long wire with currents of 1,000 amps. How much magnetic flux passes through a 1 meter square located between 4 and 5 meters from the wire? Direction of H is given by the right-hand law again. So if the current is going this way, the magnetic flux in this is going inwards, okay? Easiest way to solve the problem is to take advantage of symmetry. For an integration path, we'll choose a circle with a radius of x. Now, the key problem with the previous derivation is we assume no return path for the current. Now we consider the case of 2 wires, each carrying the same current, I, but in opposite directions. Assume the wires are separate by distance r. So the one on the left creates a counterclockwise field, and the one on the right creates a clockwise field. Again, the one on the left, the current is coming towards us, it's outwards. And if you use the right-hand law, the thumb is going to be the direction of the current. Then you can see the magnetic field is going in this direction. And the one on the right, the magnet is going inside. And according to the right-hand's law, the magnetic field is going to be clockwise. Now, what happens in between is you're going to have the magnetic field from the one on the right going upwards, and the magnetic field on the left one, it's going also upwards. So if I want to measure the magnetic field here, I have one from the first one and the other one from the second one. So if they're having the same current and this distance is also the same, you're going to double the magnetic field that you have between them. Now, if both of them are going outwards, they have the same current, the same distance, you're going to cancel them out, okay? To determine the inductance of each conductor, we integrate as before. However, now we get some field cancellation as well. And one thing that we didn't mention here is the mutual inductance between them, meaning the line on the right is going to have the magnetic field going through the line on the left, which is going upwards, and the one on the left is going to have a magnetic field going to the one on the right, which again is going upwards, okay? And that magnetic field puts another current inside that, because if you put a wire inside a magnetic field, you're going to generate some current. So sometimes that's negligible, you can just neglect that. Sometimes it's too much to be neglected. Now, for a two-conductor case, the key point as we integrate for the left line at distance 2r from the left line, the net flux linked due to the right line is 0. Use superposition to get the total flux linkage. For distance rp greater than 2r from the left line, delta left would be mu0 over 2 pi I ln of rp over r prime minus mu0 over 2 pi I ln of rp minus r over r. The left part is for the left current and the right part is for the right current. Again, can you determine, can you tell me without even calculating this, what is the magnetic field in RP? Is it going left or right? Is it going up or down? Let's say this way. So for this one, I'm going to call this I1. This is going to be I2. Down Y, because I1's effect is if they have the same current, the distance is greater than I2. Therefore, I2 is going to have a stronger flux magnetic field on that. Now, if I replace this with a wire with which the current is going past through, do you remember the right-hand law? If your fingers are the direction of the current and your thumb is the palm of your hand is the magnetic flux, then your thumb would be the direction of the force. So in this case, since it's going downwards and the current is going inside, you're going to have a force that it's pulling this wire towards. It's not pushing it away, it's pulling it towards R2, okay? So one is pushing it away, one is pulling it in. But the thing is, since I2 is closer to that, it has a stronger field on it, so it's going to get pulled toward. We don't want to measure force here, we just want to measure the magnetic flux. So if we use that equation, we're simplifying with equal and opposite currents, then I'm not going to go through the proof. L left, the lambda is going to be mu 0 over 2 pi ln of r over r prime h over m. If we have many conductor, it's going to look like this. It's going to get much more complicated. Each conductor's flux linkage, delta K, depends upon its own current and the current in all the other conductors. So they're going to have mutual, force flux on each other as well. And when it gets to this point, it becomes very, very complicated. So imagine we have one force from this, IN, one from I2, one from I1. So you're going to have multiple, different magnetic fluxes on R1. So now you assume that we now have K conductors, each with current IK, arranged in some specified geometry. We would like to find the flux linkages of each conductor. To derive lambda 1, sometimes they call delta, we'll be integrating from conductor 1 at origin to the right along the x-axis. And these are the linkages that we're going to have. Rk is the distance from conductor K to point C. At point B, the net contribution to delta 1 from Ik and delta I1k is 0. We'd like to integrate the flux crossing between B to C, but the flux crossing between A and C is easier to calculate and provides a very good approximation of delta 1k. Point A is a distance d1k from conductor K. So you can see each forces from each of the conductors. Sometimes when a conductor is too far, the effect is going to be minimal. Sometimes we just, don't consider that. And we consider the ones that are closest with the highest current, depending again on how much current we're going to have. Now, if we have many conductors, delta 1 would be mu 0 over 2 pi I1 ln of R1 over R prime 1 plus I2 ln of R2 over D1 2 until the last one, Rn over D1n. Now, as R1 goes to infinity, R1 is equal to R2 is equal to Rn. To the second term from above can be written as mu 0 over 2 pi sigma of j equal to 1 to n ij ln of R1. Now, therefore, in this case, sigma of j equal to 1 to n of ij is going to be equal to 0, which is true in a balanced three-phase system. Then the second term is 0, and delta 1 would be equal to mu 0 over 2 pi I1 ln of 1 over R prime I to plus ln of 1 over D1n. Sorry, ln of 1 over R prime, because the sigma of the currents is going to be 0. Now, delta 1 is going to be L11 I1 plus L12 I2 plus L1n IN. System has self and mutual inductance. However, the mutual inductance can be canceled for balanced three-phase systems with symmetry. Now, that's the reason what we call a bundling of a line. We put a specified spacer between these three phases, and it's maintained through the whole grid. Because if the distances change, you're going to have inductances, and it's going to, mutual inductance, and that is going to cause problem. And that's the reason you would see that all these transmission lines, they have a uniform, structure. The distances are measured, and even the three phases, when they are connected, it's a triangle form, and they have spacers that are constant for thousands of, miles, the same shape. Because if this one is this much and the next one is like this, you're going to have mutual inductance, which is going to transmit through the line, and it's going to create a lot of loss. So bundling the transmission line is a very important task. The current is the same because it's coming from some generation, and the voltage is the same. And that's the reason we keep the load balanced as well. Because if the load is imbalanced, then you're going to have different currents, and that is going to create a mutual inductance as well. So in a balanced three-phase system, we need to balance the load, the distances, and or bundling the lines as well. I'll explain more about this in the next class. We're running out of time. Thank you so much, and I'll post that second homework this weekend as well. We'll see you next week. Thank you.